Welcome everybody to our virtual set theory seminar. Today we have Calliope Ryan-Smith from the University of Leeds giving a talk on the axiom of extendable choice. Go ahead, Calliope.
Well, thank you for having me. It's great to be here. Yeah, so this talk is largely about, mathematics that can occur when choice fails, and I'm particularly interested in the structure of cardinals or cardinalities, and how cardinals and cardinalities relate to each other. Really, in many ways, this is a talk about injections and surjections. So let's, as a baseline at least, lay down some notation for this. This will be used all throughout. So fairly standard stuff. If you have two sets x and y, and you have an injection from x to y, we denote this by saying that the cardinality of x is less than or equal to y. We instead write less than or equal to star y if there's a surjection from y to x, or x is empty. And we use the usual notation, cardinality of x is equal to y if there's a bijection between these two. And a fairly basic theorem of set theory is that these two notations in fact coincide, right? There's going to be an injection from x to y if and only if there is a surjection from y to x. One of these directions is fairly straightforward in that if you have an injection from x to y, you can just take everything that isn't in the image and send that somewhere. And so instead, let me just sketch a proof of the converse. If we've got a surjection from y to x, then simply look at the fibers of this function, right? Pre-images of every individual point, and just pick one element of each of these fibers, and you'll produce an injection from x to y. And this is like the obvious remark here, of course, is that this is a theorem that relies on the axiom of choice. This action of picking an element from each of these fibers is a very fundamental use of choice. And consistently, this theorem that the less than or equal to and the less than or equal to star relations are the same can consistently fail. We have many models where this fails in ZF. Instead, this statement is in fact what we call the partition principle. So the partition principle is exactly that statement. For every set x and y, if there's an injection from x to y, then there is a surjection from y to x, and vice versa, rather. And the partition problem is the question of, does the partition principle imply the axiom of choice? And this is an open question. It is arguably the oldest open question of set theory. I believe Zumelo has writings in which he remarks upon the openness of this problem, although I forget how important he thought it was. And so indeed, when I said this remark at the top of this slide, that the theorem consistently fails in ZF, really what I should say is that for every model that we've checked, choice and the partition principle either both hold or both fail. Okay. A different structure that we have on the cardinals, or a niceness that we have on the cardinals, is another theorem, the Cantor-Bernstein theorem, that if you have an injection from x to y and an injection from y to x, then in fact there is a bijection from x to y. Again, this is a fairly easy theorem if you use the well-ordering principle. You say these are both in bijection with some aleph alpha or aleph beta and show that these ordinals must be the same. But the very nice thing about ZF is that this theorem remains true, even without the axiom of choice. So this name Cantor in the name of the theorem, which I believe some people don't include, it's a theorem with a very contentious name, I suppose. Cantor originally stated this result without proof. However, he did later produce it, rewrite it in another work, and said as a sort of proof that this is a pretty immediate corollary of the linear ordering of cardinal numbers. And by cardinal numbers here, I mean abstract cardinalities, right? These bijection classes. He said only later, well, he said it in German, but he said only later, when we better understand transfinite cardinals, will the truth become clear. All A and B, either A is equal to B, A is less than B, or A is greater than B. And I'll just translate this sort of more into our notation that we're using right now. These are exactly the same statement. I like that phrase. Only later will the truth become clear. Some number of years later, on the scale of 25, 30-ish, Hartogs publishes a paper in which we have this remarkable theorem. He shows that for every set X, there is an ordinal that cannot be injected into that set X and is not in bijection with that set X. And as a corollary, or rather, as the main theorem of his paper, as he put it, but I put it as a corollary here, we have that the axiom of choice is actually equivalent to this statement of comparability for cardinalities. So the proof is quite simple, and you've probably seen it before in set theory classes. We take a set X, we have an ordinal that cannot be injected into it. Then by this comparability assumption, we must have that X can be injected into the ordinal. X is well orderable. The well ordering principle holds, indeed. This famously is equivalent to the axiom of choice. So unfortunately, in this case, Cantor's line of reasoning was rather doomed. But this gives us a nice construction.
So can I just ask to clarify?
Yeah.
So Cantor didn't claim that this Cantor-Bendixson theorem follows from just ZF? Or, I mean, Bernstein's proof doesn't use AC, right? But Cantor, was he clear about whether this was supposed to be ZFC or ZF theorem?
From my reading of the papers, it looked like he was asserting it in ZF. But I'm not confident on that.
Okay. Okay.
But regardless of Cantor's intention, I suppose, Hartog's theorem still holds true in ZF for sure. And this gives us the excuse to define a, according to Thilo, this possibly precedes Zermelo's axiomatization. That's entirely plausible. But we can denote this Hartog's number of a set. So the Hartog's number of a set X, we're going to denote it Aleph X as the least ordinal that does not inject into a set X. And naturally, Hartog's theorem is essentially saying that Aleph X exists for every set X. And it is noteworthy that the Hartog's number of a set is always going to be some Aleph number, or finite, I suppose. Let us ignore finite sets for the moment. But yeah, at sometime later, at a similar time, a paper of Tarski and Lindenbaum comes out, including a result from Lindenbaum, a very similar result, that the axiom of choice is in fact equivalent to comparability for this surjection relation as well. And so we can also put in Lindenbaum numbers. So for set x, the Lindenbaum number of x is just going to be the least ordinal alpha such that x does not surject onto it. And note again that Lindenbaum numbers exist, and they are going to be Aleph numbers for infinite sets. And indeed, Hartog's numbers are always going to be at most the Lindenbaum numbers. So the partition principle would inform us that this property of a set having an ordinal inject into it or surjecting onto that ordinal is the same, and implies this relation that for all sets, the Hartog's number and the Lindenbaum number are the same. I'll denote this statement by just Aleph equals Aleph star. This leads to some fairly natural questions, in my opinion. So firstly, does Aleph equals Aleph star imply AC? Is that enough to get us choice? Notably, this is a harder question than the partition problem, but natural nonetheless. A different question is, does Aleph equals Aleph star imply the partition principle? The answer, of course, in both cases is no. To divulge the reason for this, I'll first need some notation. So we're just going to write WO for the class of well-orderable sets and AC well-order to mean the axiom of choice for well-orderable sets. So if you're well-orderable, you don't contain the empty set, then you have a choice function. And so we have two theorems of Pincus that answer this question negatively in two separate papers. One is a paper by Pelk, but he attributes the results to Pincus. Firstly, that this statement, Aleph is equal to Aleph star, is equivalent to well-orderable choice. And secondly, Pincus produced a model of ZF in which well-orderable choice holds, but choice fails, and indeed the partition principle fails. A very standard structure for an independence proof. This is the bread and butter of set theory in many ways. But this first, this theorem, or these two, this theorem, I think, deserves some closer attention. Hopefully you agree with me, because I'm going to talk about it for another however long. And so I think it is quite reasonable to sketch through a proof of this. Firstly, the sort of easier direction is the backwards one. So you take some ordinal alpha and assume that you have a surjection from x onto alpha, and it's by some function f. Then by well-orderable choice, we can do exactly as we started. You can pick an element of each of the fibers of this function to get an injection from alpha to x, right? So if you are less than Aleph star of x, then you're less than Aleph x. These two quantities must be the same.
Oh, no. That's the inequality.
Pardon?
Oh, but you chat.
The other direction is a bit more involved, which you can probably tell because the proof box is larger. So we're going to do an induction. We're just going to assume the axiom of choice for families of sets that can be indexed by something less than Aleph delta, some delta. We're going to take such a family, well, we're going to take a family of sets of non-empty sets indexed by Aleph delta. And basically, we just want to show that there is a choice function for this family. By our assumption, what we can do is take initial segments of this family and know that each of these have choice functions, right? So y alpha is going to be the choice functions for the first alpha many sets in this family. And these are all non-empty. So we can inductively define quantities kappa alpha and sets d alpha by taking kappa alpha to be the Hartog's number of all of the union of all of the d alphas we've produced thus far, I suppose d betas, and then defining d alpha to be just y alpha times kappa alpha. We'll take d itself to just be the union of all of these, and lambda to be the supremum of all these kappa alphas. So note that if we simply project this set D is a bunch of doubles. If we project it onto its second coordinate, every element, then we obtain a surjection onto lambda, essentially by definition. So by our assumption that Aleph is equal to Aleph star, we must in fact have an injection from lambda into our set D. So I'm going to propose that we can use this to produce just a choice function for x. So firstly, f of 0 is going to be some g0 epsilon naught, where g0 is a choice function. What is d beta? What is d beta? Oh, so the ordering of these two inductive definitions looks kind of backwards, but note that kappa 0 is going to be Aleph empty set, which is 1, and then d0 is going to be y0 times 1, and then you start having actual inductive definitions. So kappa 1 is going to be the Hartog's number of d0, and then d1, etc. Right. Anyway, we've got ourselves an injection from lambda to d. So where rather than and? We proceed inductively defining kappa alpha first and then d alpha. Since kappa alpha uses the sets d beta for beta less than alpha, and d alpha uses kappa alpha. In this way, we keep everything well defined, well founded. So f of 0 is going to be some g0 epsilon naught, where g0 is, as I say, a partial choice function for this set x, an initial segment. And epsilon naught is some ordinal. It's not going to matter. What I'm going to say is for every alpha in the domain of this g0, I'm going to let x alpha be g0 of alpha. Little x alpha is going to be g0 of alpha, which is going to be an element of capital X alpha by definition. And basically, we're just going to do this, repeat this process for everything in the domain of f. So in fact, we're going to just define little x alpha to be g beta of alpha, where beta is least such that alpha is in the domain of g beta. So if this is well defined, then we're done. We have a choice function for this family x. Otherwise, this f must be an injection from lambda into some initial segment of these d betas. All of the d betas less than alpha, say. But by construction, lambda is going to be at least kappa alpha, which is at least the Hartog's number of this union. And so simply by definition, lambda, there is no injection from lambda into this bounded initial segment of these d betas. which poses a contradiction. So in fact, this is well defined. You can actually sort of tweak this proof to show that, use this to take sets where you know that the Hartog's number is strictly smaller than the Lindenbaum number and sort of lift them to sets with larger Hartog's numbers that still are smaller than the Lindenbaum number. There's a lot of interesting mining to be done in this proof. Now, I quite like this result. And one of the reasons is I feel like it's a sort of ordinary partition problem. So the partition problem, again, is the question, does the statement for all x and y, if there's a surjection from y to x, then there's an injection from x to y, imply the statement for all x, if the empty set isn't in x, then x has a choice function? Whereas this theorem of Pincus says it is the case that the statement for all well-orderable x and all y, if there is a surjection from y to x, then there is an injection from x to y, implies the statement for all well-orderable x, not containing the empty set, x has a choice function. Now, I mean, strictly speaking, this is just in some ways an aesthetic similarity, but I like to feel like this is a genuine facet of the partition problem being solved. So this theorem of Pincus gives us a alternative characterization of well-orderable choice. It says that if well-orderable choice fails, then there has to be a set x with Hartog's number less than the Lindenbaum number, which leads me to define the Hartog's Lindenbaum spectrum. So for a model of ZF, the Hartog's Lindenbaum spectrum of that model is the class of all pairs Aleph x, Aleph star of x for every set x. Equivalently, the class of all pairs lambda kappa, where there is some set x such that the Hartog's number of x is lambda and the Lindenbaum number of x is kappa. Note, for example, that we always have the successor pairs of Aleph numbers contained in this spectrum. Because if you take a well-orderable set X, let's say we take Aleph alpha itself, right? Then the Hartog's number of Aleph alpha is the least ordinal that does not inject into it. This is definitionally Aleph alpha plus 1. And similarly for surjections, you very easily obtain that the Lindenbaum number of Aleph alpha is Aleph alpha plus 1. But this theorem of Pincus tells us that well-orderable choice is equivalent to this spectrum being contained in the diagonal, so to speak. And in fact, a result of my own is that well-orderable choice is equivalent to the spectrum being exactly these successor pairs. So there is no way to have well-orderable choice, but a limit Hartog's number, for example. So this...
Of course not.
Indeed. Of course not. I mean, for many of these things, you take the axiom of choice proof and you just do it and then see that it's really not only using well-ordered choice. But this gives us a way to analyze failures of well-ordered choice in terms of these spectra. So one question can be, for example, how wild can a spectrum be? We know that there are indeed models of ZF that fail well-ordered choice, and so there must be sets with greater Lindenbaum number than Hartog's, but is there any kind of bound on this? And one answer comes in the form of a theorem by myself. Yes, Lovey.
Hi.
yes.
Sorry, is there something funny going on with the finite numbers here, or are you considering Aleph 0 to be like 0 or something like that, or am I?
Oh, you're quite right. No, the sub here should include n plus 1, comma n plus 1.
Okay. Okay.
Yeah. So finite numbers, yeah. Yeah, so a finite set is always going to have Hartog's and the bound numbers be equal to the successor of its cardinality. And indeed, we are going to always have that, yeah.
Thanks.
No problem. I suspect that the rest of my slides similarly forget about the existence of finite sets. I'm whatever the opposite of an ultra-finitist is, I suppose. So Adam asks, is this really about models or is it actually syntactic? This is syntactic. The spectrum is a definable class of pairs of cardinals, and really we are asking internally, what does M think these Hartog's and Lindenbaum numbers are? So it turns out the spectrum can get pretty wild. So one theorem of myself and Asaf Karagila is that there is a model of ZF where the spectrum is all valid pairs of cardinals, plus the finite ones. So it turns out that the restrictions that we have mentioned, so Hartog's and Lindenbaum numbers are both always well-orderable cardinals. The Hartog's number is at most the Lindenbaum number. And if they are finite, then they are both equal and non-zero. But that is all that you can actually prove about them in that sense. So you can get a model of ZF where the spectrum is every such pair, which is nice, it's fun, but is in some sense a bit of overkill. So let's instead look at our favorite testing grounds for choiceless mathematics, Cohen's first model, or Cohen's first model of not choice, if you prefer. This compared to the prior model is a very tame model of choiceless mathematics in many ways. So this is a model of ZF that lies between L and L with countably many Cohen reals attached. And in fact, it is L with adjoined or with the set A included, where A is simply the set of all of these Cohen reals. Right? And we like to say, we like the personification where we think of these choiceless models as forgetting information. We often say that Cohen's first model, you add omega many Cohen reals, but you forget the enumeration. And indeed, this has some truth to it, because in M, this set A is infinite, right? So there are injections from every finite ordinal into the set, but there is no injection from Aleph naught into the set A. It is so-called Dedekind infinite. Conversely, it is a ZF theorem that every infinite set of reals surjects onto Aleph naught. And so in fact, we have ourselves a set A with Hartog's number Aleph naught and larger Lindenbaum number. And in fact, it's equal to Aleph 1. So we know for a fact, at least in Cohen's first model, the spectrum contains all of these successor pairs and the pair Aleph naught, Aleph 1. But in fact, the spectrum of Cohen's first model is in many ways extremely tame. So we have all of these successor pairs, and the only non-equal, so-called eccentric sets where the Hartog's number is less than the Lindenbaum number, the only time that occurs is when we have lambda and lambda plus for countable cofinality lambda. So there are no Lindenbaum numbers that are, two successors greater than the Hartog's number. There are none of uncountable cofinality. This presents a kind of tension in the statement that Cohen's first model fails well-orderable choice. So on the one hand, we have the very reasonable assertion here that Cohen's first model fails well-orderable choice dramatically. It is not even a model of countable choice. If well-orderable choice is, the statement AC alpha for all ordinals alpha, then Cohen's first model fails this immediately and for as many alphas as possible. But on the other hand, through this sort of spectral analysis, so to speak, it seems, at least to me, that Cohen's first model fails in a very gentle way. There isn't that much eccentricity in the model. This is reconciled by, well, the titular extendable choice. So we're going to let alpha be some ordinal and say that a family X, indexed by this alpha, so a function if you prefer, of sets is going to be alpha approachable if, well, it does not contain the empty set, and all initial segments of this family have choice functions. So even if this family itself doesn't have a choice function, we can always cut it off anywhere and produce a choice function for it. And the axiom of extendable choice for alpha, EC alpha, is the statement that every alpha approachable family, in fact, has a choice function. You can always stitch these partial choice functions together in some way to produce a choice function for the whole family. This was originally introduced by Levy in 64. The paper's called something like on some interdependencies of things in mathematics. I have a references slide. He originally did not put a name for it, and in fact used the notation C of alpha. I thought that might be not exactly where modern set theory notation has gone. So I introduced the name extendable choice and EC alpha. Interestingly, what we would normally call AC sub alpha, axiom of choice for alpha indexed sets, is he wrote C star alpha. Anyway, in this paper, he proves a huge amount about extendable choice and dependent choices and the axiom of choice. It's a very important paper. I believe it is the first formulation of the generalization of dependent choice. Yes. And indeed, he proves things like, for example, and this one's fairly clear, EC0. We have extendable choice for all successor ordinals. And reasonably importantly, if two ordinals are cofinal with one another, then extendable choice holds for one if and only if it holds for the other. This isn't too difficult to prove. It's a fun exercise if you'd like. Furthermore, he shows that in some sense you cannot, he shows that you cannot deduce anything else about EC from just two ordinals. So for all non-zero limit ordinals, alpha and beta, that aren't cofinal with each other, he produces a model of ZF. I mean, he produces a model of ZFA, but look at the date, where extendable choice holds for one and fails for the other. So these are very independent properties otherwise. Furthermore, it's worth noting that choice for families of size less than Aleph alpha is equivalent to extendable choice on all of those ordinals. And indeed, well-ordered choice is equivalent to just having EC alpha for all alpha. much as the same as it is equivalent to having AC alpha for all alpha. Now, this point number 3 is quite interesting, and in fact, sort of hints at the way that extendable choice here is related to this spectral analysis. So theorem of my own is that if we take a regular cardinal, as in we may as well take a regular cardinal, and I'm just going to use capital CF kappa to denote the class of all cardinals with cofinality kappa, then the following are going to be equivalent, right? We've got a failure of extendable choice at kappa is the same as saying that there is some set X with limit Hartog's number of cofinality kappa, is in fact the same as saying that there's a cardinal mu with cofinality kappa such that for some set, the Hartog's number is mu, and that is less than the Lindenbaum number. And in fact, these are all equivalent to saying that this happens on a all large enough mu of cofinality kappa. And so this spectrum of the Cohen's first model, right? Here it is. This fact that we have this proper class of pairs, lambda, lambda plus, for countable cofinality lambda, is necessary when we've got a failure of EC omega. And indeed, this spectrum tells us that extendable choice holds everywhere except countable cofinality ordinals. And this is my argument for the idea that Cohen's first model fails well-ordered choice very gently. Even though it fails it already at omega, it really only fails it at omega. If you give me a Aleph 1 indexed family of sets and you have partial choice functions for all of the initial segments, then you have a choice function for that family. And this is probably reasonably easy to show with the sort of either the symmetric extension or the inner model definition of this model, because of definitions. But yeah, this is a sort of reconciliation of this idea. So can we do something similar for other cofinalities? So let's say we, instead of saying we only want EC to fail at countable cofinality, what if we want it to only fail at cofinality omega 1, or both of these? And indeed, we have almost total control over for which cofinalities we can make extendable choice fail. So if we assume GCH, and we take any class of regular cardinals, that is closed under regular limits. So any class of regular cardinals, but if it is unbounded below a inaccessible cardinal, that inaccessible cardinal has to be included as well. Then in fact, we can produce a model of ZF with spectrum being these successor pairs and lambda, lambda plus, where whenever the cofinality of lambda is in this class. And indeed, in particular, extendable choice fails exactly on ordinals with cofinality in that class. The closure under regular limits here is just an artifact of the construction. Yeah, Levy.
Hi, yeah, just to make sure I understand this. So by class, when you say CB a class, you mean like a definable class that's provably closed under regular limits? And then I should read the next thing, because otherwise I don't know how to understand the rest of the statement.
Yeah. So really, definable is definitely enough. Yeah, the definable, it doesn't need to be provably closed inside the model V, but it does. So we want a concrete model of ZFC plus GCH. Definable classes are going to work with this, yes. So we want some definable class, and thinking in a sort of Platonic sense, that model V, that class is either going to be closed under all regular limits or not. But really, the definition of class required for this result is thing that makes, well, subset of the model that does not violate ZF when you add it as a definable class to the model. Thing that makes maths not, that makes the symmetric extension not violate ZF. So yeah, you could not take a set model of ZFC and plus GCH and take, I don't know, a cofinal omega sequence of regular cardinals in the model, because yeah, then you have this definable class in the extension that is a countable cofinal sequence of ordinals. We don't like those in ZF. So yeah, definable is always fine. And I strongly suspect that there are other classes you can throw in.
Okay, so definable is too restrictive.
Yeah, there will be non-definable classes for which you can do this construction. They will just become definable in the extension.
Okay. Right. Okay, thanks.
But yes. So with the last little bit of the talk, let's talk about a slightly different cardinal structure. So I'm going to use this fractor C to represent the class of all cardinal numbers in a vaguely defined sense. This is the equivalence classes of cardinality, very anti-centennial set theory, rather than just well-orderable cardinals. So the theorem of Hartog's from his paper is that the axiom of choice is equivalent to the linear ordering, this class structure, you know, C less than or equal to being a linear order. Or indeed, it's equivalent to this relation be having comparability or trichotomy, but we very quickly get back a linear order from that. And the theorem of Lindenbaum is that choice is equivalent to this structure, but with the surjection relation being a linear order. So what happens when this fails, right? So let's think about the injection relation, right? The less than or equal to. We cannot assume that it has this trichotomy property in ZF, but it is certainly reflexive, it is certainly transitive, and indeed, by the theorem about injections between sets, it doesn't have a loops, it's separative. Indeed, the C less than or equal to here must be a class partial order, let's say. C less than or equal to star needn't have that separativity. It can have non-trivial loops. You can have sets A and B, each surjecting onto the other, but not in bijection. There's an easy example in the Solovay model, I think. But there are also sets that surject onto their powers, or no, there's a surjection from the square of a set onto its power, and you can do something with this. But oftentimes we do still find that it is a partial order. So one theorem of Yex is that if we want to, we can take any set-sized partial order and find a model of ZF in such that that partial order embeds into the cardinal structure. This is preserving both less than or equal to and not less than or equal to. We're not just putting a linear order on this. This was originally done in ZFA, and it was done with set sized P, but both of these have been extended, so you can quite easily do this in ZF proper. And you can do it with class partial orders for some well enough defined notion of class partial order. Later on, Asaf Karagila did the same work, but with the less than or equal to star relation, showing that you can actually embed any arbitrary partial order into C less than or equal to star, as well as pushing this a bit further, including classes in some sense, and while preserving as much DC as you want, I believe. Then, very recently, we have a result of Shen and Zhou, which shows that you can sort of do both at the same time if your requirements are nice enough. So they showed that for all so-called doubly ordered sets, that is to say, we've got a partial order P less than or equal to, and a pre-order P less than or equal to star that extends the partial order. So for any such doubly ordered set, you can find a model of ZF for which that double order embeds into C less than or equal to star. I believe they haven't done this with class-sized doubly ordered sets or while preserving DC, but the paper indicates ways to do this. It should be not too difficult. And so, yes, when we break away from the axiom of choice, we can get reasonably strange and arbitrary structures appearing in cardinals. So what else is there to do? Well, I would like to see some finer control over the Hartog-Lindenbaum spectrum. So we have a lot more now on what can appear and what must appear, but in many ways, a lot of the work is still somewhat primitive. So could we, for example, remove this assumption that, it's over here, this assumption that this class C is closed under regular limits? We cannot with the construction that I used. It's just a result of the construction that you will fail EC at regular limits, closures under regular limits. But can we construct the model better to avoid this? Or, can we start these lambda pluses later? Could we say lambda plus where the cofinality of lambda is in C, but lambda itself is not in C, so only for limits of cofinality in C. This sort of thing. Could we have a gap somewhere in the middle? So could I have a spectrum that has all the successors plus, let's say, aleph1 and comma aleph2, and then aleph1 comma aleph1 plus 1, and then everything later than that, but with this huge gap in the middle. How can we embed more general structures into cardinals? So an example is so-called cardinal algebras, which I believe were primarily introduced by Tarski. The class of cardinals does produce a cardinal algebra, but can we embed any cardinal algebra into the cardinals? I'd like to understand how extendable choice is affected by large cardinal properties of kappa. So we have some very basic results. I believe if kappa is a super compact cardinal in the usual choiceless phrasing of super compactness, then if you have extendable choice below kappa, which is equivalent to AC less than kappa, then axiom of choice holds. I believe this is known forever. And similarly, if you have extendable choice failing everywhere below kappa, then I believe it has to fail It's either everywhere or on a proper class of cardinals, of regular cardinals. But super compact cardinals are pretty large for some. I would love to know more about more tame large cardinals, Marlows and inaccessibles, measurables even, or critical cardinals. And localizing all of this to SVC would be nice for those familiar. SVC, for those not, briefly is a very nice statement that choice is only slightly violated in some ways. It is equivalent to saying that you are an inner model of a model of ZFC of the form, V round brackets A for some set A and V a model of ZFC, or equivalently that you're a set generic symmetric extension of a model of ZFC. And many nice choiceless properties have very nice local characterizations under this assumption. I'd like to know more about that. And my remaining slides are just references. So thank you for listening.
Thank you. Very interesting. Okay, are there any comments or questions?
Yes, I would have one.
Go ahead. Is it Thilo? Or?
Yes, I'm Thilo. Hi.
Okay.
Thank you for your talk, Calliope. I'm just curious, the restriction, or you mentioned the restriction of the axiom of choice to well-ordered sets. Is there anything interesting to say about the restriction of the axiom of choice to linearly orderable sets?
This has been looked at a bit, I believe. This appears in, I believe that the statement, ACLO, let's say, appears in Consequences of the Axiom of Choice by someone and Rubin.
Howard.
Howard, thank you so much. Howard Rubin. But I don't know that much has been done in terms of an analysis like this. I'm not sure what it would look like even. I suppose you could start making sort of aesthetic connections, looking at... So a way to define the Hartog's number is the set of all ordinals for which there is an injection from that ordinal into the set. You could start defining classes of first order structures like this, but I'm not sure where to go outside of these aesthetic connections.
All right. So it's, I would imagine it's pretty clear that the results that you mentioned, it's not clear how that would work with this principle, or yeah.
Yeah, yes. So I mean, linearly ordered choice is stronger than well-ordered choice. So you'd need some other construction, but it's a lot of the work with AC well-ordered uses fully inductive proofs on these well-orderable families. And so the well-ordering is very fundamental to the nature. It's not, yeah.
Yeah, okay, yeah, thank you.
Blas.
Andreas, yes?
Yeah, I had a question. Actually, I think I have several questions, but then they all have the same answer. I noticed at first on, I think it was slide 13, where you had theorem of Levy about models where you see alpha holds. Oops.
Oh, this one.
Something like that. There were some models, where you can have EC in some places and not EC in others. And I believe I heard you say that he was actually using set theory with atoms, which makes sense because the paper was 1964. There had not been enough time to do very much with forcing. I gather from that once you have a model with atoms, the usual transfer theorems will get you the same result in ZF without atoms. And that certainly is fine. The Sohor theorem will take the transfer of the negation of EC. As for transferring the positive half that EC holds for certain alphas, if somebody asked me, how do you transfer that? I would say, read the collected works of Pincus. Now, is that in fact the right answer, or is there something easier than the collected works of Dave Pincus to do this?
Yeah, you could probably don't need to read in the entirety of the collected works of Pincus. It should be
reduce it to the first two papers, which I think were essentially his thesis. So essentially where he gets these transfer theorems for injectively boundable and that kind of thing.
Yeah, I believe that it should be injectively boundable or possibly surjectively boundable. I do believe that this should be a transferable result using some reasonably established technology of the form. At the very least, using very, very modern characterizations of EC, we can show that it should be transferable in the positive.
Okay.
But my constructions, so I did start looking at his construction for this to have a look at it, and I did not get very far, because this was at a time when the axioms of set theory were written as the letters A through G, and also the notation was difficult to get through. So I ended up making my own models, and in those cases, I don't use atoms. I go directly with symmetric extensions and just prove directly that EC does or doesn't hold, which I found easier.
Maybe I should say something about it. I did that once too, tried to read those, essentially the first two papers of Pincus, with the idea of, okay, I can read the theorems, but what are the actual models that he uses? And I convinced myself that he was using the same models as the Sohor theorem. So he wasn't building new models, he was just proving better properties of the already known models. I'm not 100% sure that I was right about that. I certainly haven't tried to write it out carefully, but as I say, I convinced myself that that was what was going on.
Yes, it's. I admit so when I read, for example, I convinced myself that it is quite accurate to say that this second result of Pincus is indeed a result of Pincus. But I forget if this is a model that he was producing for other reasons, and then someone else later proved that well-ordered choice holds. I don't think that's the case, but
no, that's certainly how I understood
okay.
these results, that they were really Pincus's.
Yeah. This first one is quite interesting as well. It's the actual lemma in the paper is that the partition principle implies Aleph equals Aleph star, but the mathematical community has noticed that he only uses well-ordered choice and that the other direction is pretty obvious. And so this entire result is attributed to Pincus.
Okay. Well, thank you.
Maybe I also have a quick question. So just thinking about this concept of extendable choice, there seems to be a related strengthening of this. So, for example, if you so it would say basically if you have an increasing sequence of if you can write a set as an increasing union of length alpha of non-empty sets, each of which has of sets of non-empty sets, each of which has a choice function, then the whole thing, the whole union has a choice function, right? So instead of, so it's seems quite a bit stronger, but I wonder, is it related? Is it the same? Is it?
So you write a set as a increasing union of sets of non-empty sets.
Yes.
And each of those individual sets has a choice function.
Yes.
Then the whole thing does. That is most likely.
Does it imply AC?
For all alpha, yes, probably, or well-ordered choice. But I think that's likely to be equivalent. So you do a lot of tricks like this.
Mm-hmm.
So if we wanted to prove that EC is EC alpha if and only if EC beta, when alpha and beta are of the same cofinality.
Exactly. That's why I was thinking
then
it might,
just
be the same.
Yeah.
Uh-huh.
Like you just rewrite your larger family of sets as being a set of partial choice functions. I imagine we can do much the same. But I would have to write down the details.
Mm-hmm.
It does have some sort of strengthenings. It's interesting. It's a sort of DC. It looks to me like a DC sort of statement, even though it's in some senses closer to AC alphas. Where if you think of the tree of partial, of initial choice functions, and this is sort of saying if this tree has enough levels, then it has a branch.
Right. Mm-hmm.
But yeah, I think depending on the exact way that you state that axiom, it is either going to be equivalent to choice, equivalent to well-ordered choice, or just equivalent to extendable choice at some ordinal.
Okay. Okay. Any other comments or questions?
I don't have a question, but I just wanted to say that great talk. Thank you so much. I really enjoyed it.
Thank you.
Okay.
Yeah, it's a lot of fun to put together.
That's me too.
All right. Yeah. Thanks from all of us. Very, very interesting talk.